itself from data. Just one note, in this visualization, the neurons in the first hidden layer are shown looking at relatively small windows to look for these edges. And then the second hidden layer is looking at a bigger window, and the third hidden layer is looking at an even bigger window. So these little neurons visualizations actually correspond to differently sized regions in the image. Just for fun, let's see what happens if you were to train this neural network on a different data set. Say on lots of pictures of cars pictured on the side. The same learning algorithm, if is asked to detect cars, will then learn edges in the first layer, so pretty similar, but then they'll learn to detect parts of cars in the second hidden layer, and then more complete car shapes in the third hidden layer. So just by feeding it different data, the neural network automatically learns to detect very different features so as to try to make the predictions of car detection or person recognition or whatever is a particular given task that is trained on. So that's how a neural network works for a computer vision application. And in fact, later this week, you'll see how you can build a neural network yourself and apply it to a handwritten digit recognition application. So far, we've been going over the description of intuitions of neural networks and therefore how you can implement one of these things yourself. Let's go on to the next video.
Hey learner, excited about this course? Join the deeplearning.ai forum to report any trouble with assignments. Get support for any technical issues you might have with the course platform. Look for guidance on any questions you might have about the course.
bracket 1. So this, the fundamental building block of most modern neural networks is a layer of neurons. In this video, you learn how to construct a layer of neurons. And once you have that down, you'll be able to take those building blocks and put them together to form a large neural network. Let's take a look at how a layer of neurons works. Here's the example we had from the demand prediction example, where we had 4 input features that were fed to this layer of 3 neurons in this hidden layer that then sends its output to this output layer with just 1 neuron. Let's zoom in to the hidden layer to look at its computations. This hidden layer inputs 4 numbers, and these 4 numbers are inputs to each of 3 neurons. And each of these 3 neurons is just implementing a little logistic regression unit or a little logistic regression function. So take this first neuron. It has 2 parameters, W and B. And in fact, to denote that this is the first hidden unit, I'm going to subscript this as W1, B1. And what it does is it'll output some activation value A, which is G of W1 in a product with X plus B1, where this is the familiar Z value that you had learned about in logistic regression in the previous course. And G of Z is the familiar logistic function, 1 over 1 plus e to the negative z. And so maybe this ends up being a number 0.3, and that's the activation value A of the first neuron. To denote that this is the first neuron, I'm also going to add a subscript A1 over here. And so A1 may be a number like 0.3. There's a 0.3 chance of this being highly affordable based on the input features. Now let's look at the second neuron. The second neuron has parameters W2 and B2, and this WB or W2B2 are the parameters of the second logistic unit. So it computes A2 equals the logistic function G applied to W2 dot product X plus B2, and this may be some other number, say 0.7, because in this example, there's a 0.7 chance that we think the potential buyers will be aware of this t-shirt. And similarly, the third neuron has a third set of parameters, W3, B3, and similarly computes an activation value A3 equals G of W3 dot product X plus B3, and that may be, say, 0.2. So in this example, these 3 neurons output 0.3, 0.7, and 0.2, and this vector of 3 numbers becomes the vector of activation values A that is then passed to the final output layer of this neural network. Now, when you build neural networks with multiple layers, it'll be useful to give the layers different numbers. So by convention, this layer is called layer 1 of the neural network, and this layer is called layer 2 of the neural network, and the input layer is also sometimes called layer 0. And today, there are neural networks that can have dozens or even hundreds of layers. But in order to introduce notation to help us distinguish between the different layers, I'm going to use superscript square bracket 1 to index into different layers. So in particular, A, superscript in square brackets 1, I'm going to use as a notation to denote the output of layer 1 of this hidden layer of this neural network. And similarly, W1, B1 here are the parameters of the first unit in layer 1 of the neural network. So I'm also going to add a superscript in square brackets 1 here. And this is, and W2, B2 are the parameters of the second hidden unit or the second hidden neuron in layer 1. And so its parameters are also denoted here, W superscript square bracket 1, like so. And similarly, I can add superscript square brackets like so to denote that these are the activation values of the hidden units of layer 1 of this neural network. I know maybe this notation is getting a little bit cluttered, but the thing to remember is whenever you see this superscript square bracket 1, that just refers to a quantity that is associated with layer 1 of the neural network. And if you see superscript square bracket 2, that refers to a quantity associated with layer 2 of the neural network. And similarly for other layers as well, including layer 3, layer 4, and so on for neural networks with more layers. So that's the computation of layer 1 of this neural network. Its output is this activation vector, A superscript square bracket 1. And I'm going to copy this over here because this output A1 becomes the input to layer 2. So now let's zoom into the computation of layer 2 of this neural network, which is also the output layer. So the input to layer 2 is the output of layer 1. So A1 is this vector 0.3, 0.7, 0.2 that we just computed on the previous part of the slide. And so because the output layer has just a single neuron, all it does is it computes A subscript 1, that is the output of its first and only neuron, as G, the sigmoid function, applied to W subscript 1 in a product with A superscript square bracket 1. So this is the input into this layer, and then plus B1. Here, this is the quantity Z that you're familiar with, and G, as before, is the sigmoid function that you apply to this. And if this results in a number, say 0.84, then that becomes the output of this output layer of the neural network. And in this example, because the output layer has just a single neuron, its output is just a scalar, as a single number rather than a vector of numbers. Sticking with our notational convention from before, we're going to use A superscript in square brackets 2 to denote the quantities associated with layer 2 of this neural network. So A superscript square bracket 2 is the output of this layer. And so I'm going to also copy this here as the final output of the neural network. And to make the notation consistent, you can also add these superscript square bracket 2s to denote that these are the parameters and activation values associated with layer 2 of the neural network. Once the neural network has computed A2, there's one final optional step that you can choose to implement or not, which is if you want a binary prediction, 1 or 0, is this a top seller, yes or no, is you can take the number A superscript square brackets 2 subscript 1, and this is the number 0.84 that we computed, and threshold is at 0.5. So if it's greater than 0.5, you can predict y hat equals 1, and if it's less than 0.5, then predict y hat equals 0. And we saw this thresholding as well when you learned about logistic regression in the first course of the specialization. So if you wish, this then gives you the final prediction y hat as either 1 or 0 if you don't want just a probability of it being a top seller. So that's how a neural network works. Every layer inputs a vector of numbers and applies a bunch of logistic regression units to it, and then computes another vector of numbers that then gets passed from layer to layer until you get the final output layer's computation, which is a prediction of the neural network that you can either threshold at 0.5 or not to come up with the final prediction. And with that, let's go on to use this foundation we've built now to look at some even more complex, even larger neural network models. And I hope that by seeing more examples, this concept of layers and how to put them together to build a neural network will become even clearer. So let's go on to the next video.
一曲定重楼，一眼半生愁，看的全都是那贵贱云游。入得此门不回首，无需宣之于口。我对岸再摆那风雨漂泊的残楼杯依旧。戏子多秋，可怜一出青山旧，满座衣冠皆老朽，黄泉故事无知休。对镜遮掩那风雨漂泊的残楼杯酒。戏子多秋，可怜一出青山旧，满座衣冠皆老朽，黄泉故事无知休。难舍难分难解，缘起缘结缘灭。送给你不仅有那木错的风，还有那拉冷山的雨，就像你流下眼泪的声音，融化雪一样的冬季。错过了日出，我就等你看日落；错过了雪花，我就等你看雪落。没赶上花开，我就等你看花落；没赶上今生，我就等轮回。今生相见你。 不见，今生不见。迎接你不仅有那无措的泪，还有拉萨黑的水，就像你臂弯宁静的夜晚，所有灯下你有多美，星星在枝头，云朵替我在挽留，谷笛声轮袖，想你我就能吹走。试过多少种让你微笑的理由，试过多少回你一去没回头。Los Tonka, Los Tonka, Tonka, Las Palmas, Las Palmas Park， 今生相见定有亏欠，前世不见，今生不见。山峰啊，请把雪山融化，带你看看柳斑给苍花。
In the last video, you learned about the neural network layer and how that takes as input a vector of numbers and in turn outputs another vector of numbers. In this video, let's use that layer to build a more complex neural network. And through this, I hope that the notation that we're using for neural networks will become clearer and more concrete as well. Let's take a look. This is the running example that I'm going to use throughout this video as an example of a more complex neural network. This network has 4 layers, not counting the input layer, which is also called layer 0, where layers 1, 2, and 3 are hidden layers, and layer 4 is the output layer, and layer 0, as usual, is the input layer. By convention, when we say that a neural network has 4 layers, that includes all the hidden layers in the output layer, but we don't count the input layer. So this is a neural network with 4 layers in the conventional way of counting layers in the network. Let's zoom in to layer 3, which is the third and final hidden layer, to look at the computations of that layer. Layer 3 inputs a vector, a superscript square bracket 2 that was computed by the previous layer, and it outputs A3, which is another vector. So what is the computation that layer 3 does in order to go from A2 to A3? If it has 3 neurons, or we call it 3 hidden units, then it has parameters W1B1, W2B2, and W3B3, and it computes A1 equals sigmoid of W1 dot product with this input to the layer plus B1, and it computes A2 equals sigmoid of W2 dot product with, again, A2, the input to the layer, plus B2, and so on, to get A3. And then the output of this layer is a vector comprising A1, A2, and A3. And again, by convention, if we want to more explicitly denote that all of these are quantities associated with layer 3, then we add in all of these superscript square brackets 3 here to denote that these parameters W and B are the parameters associated with neurons in layer 3, and that these activations are activations with layer 3. Notice that this term here is W1 superscript square bracket 3, meaning the parameters associated with layer 3 dot product with a superscript square bracket 2, which was the output of layer 2, which became the input to layer 3. So that's why there's a 3 here, because there's a parameter associated with layer 3 dot product with, and there's a 2 there, because it's the output of layer 2. Now, let's just do a quick double check of our understanding of this. I'm going to hide the superscripts and subscripts associated with the second neuron. And without rewinding this video, go ahead and rewind if you want, but prefer you not. But without rewinding this video, are you able to think through what are the missing superscripts and subscripts in this equation and fill them in yourself? Why don't you take a look at the in-video quiz and see if you can figure out what are the appropriate superscripts and subscripts for this equation over here. here. If you chose the first option, then you got it right. The activation of the second neuron at layer 3 is denoted by A32. To apply the activation function G, let's use the parameters of this same neuron. So W and B will have the same subscript 2 and superscript square bracket 3. The input features will be the output vector from the previous layer, which is layer 2. So that will be the vector A superscript 2. The second option is using vector A3, which is not the output vector from the previous layer. The input to this layer is A2. And the third option has A22 as input, which is just a single number rather than the vector. Because recall that the correct input is a vector, A2 with the little arrow on top and not just a single number. So to recap, A3 is activation associated with layer 3 for the second neuron, hence it's a 2. There's a parameter associated with the third layer for the second neuron. This is A2, same as above, and then plus B32. So hopefully that makes sense. Here's the more general form of this equation for an arbitrary layer L and for an arbitrary unit J, which is that A, the activation output of layer L unit J, like A32, that's going to be the sigmoid function applied to this term, which is the weight vector of layer L, such as layer 3, for the jth unit. So that's 2 again in the example above. And so that's dot producted with a deactivation value of, and notice this is not L, this is L minus 1, like the 2 above here, because you're dot producting with the output from the previous layer, and then plus B, the parameter for this layer for that unit J. And so this gives you the activation of layer L's unit J, where the superscript in square brackets L denotes layer L and the subscript J denotes unit J. And when building neural networks, unit J refers to the jth neuron. So we use those terms a little bit interchangeably, where each unit is a single neuron in a layer. G here is the sigmoid function. In the context of a neural network, G has another name, which is also called the activation function, because G outputs this activation value. So when I say activation function, I mean this function G here. And so far, the only activation function you've seen is the sigmoid function. But next week, we'll look at when other functions than the sigmoid function can be plugged in place of G as well. But so the activation function is just that function that outputs these activation values. And just one last piece of notation. In order to make all this notation consistent, I'm also going to give the input vector X another name, which is A0. So this way, this same equation also works for the first layer, where when L is equal to 1, the activations of the first layer, that is A1, will be sigmoid times the weights dot product with A0, which is just this input feature vector X. So with this notation, you now know how to compute the activation values of any layer in a neural network as a function of the parameters as well as the activations of the previous layer. So you now know how to compute the activations of any layer given the activations of the previous layer. Let's put this into an inference algorithm for a neural network. In other words, how to get a neural network to make predictions. Let's go see that in the next video. Let's take what we've learned and put it together into an algorithm to let your neural network make inferences or make predictions. This will be an algorithm called forward propagation. Let's take a look. I'm going to use as a motivating example handwritten digit recognition. And for simplicity, we're just going to distinguish between the handwritten digits 0 and 1. So it's just a binary classification problem where we're going to input an image and classify, is this the digit 0 or the digit 1? And you get to play with this yourself later this week in the practice lab as well. For the example on the slide, I'm going to use an 8 by 8 image. And so this image of a 1 is this grid or matrix of 8 by 8 or 64 pixel intensity values, where 255 denotes a bright white pixel and 0 would denote a black pixel, and different numbers are different shades of gray in between the shades of black and white. Given these 64 input features, we're going to use a neural network with 2 hidden layers, where the first hidden layer has 25 neurons or 25 units. Second hidden layer has 15 neurons or 15 units. And then finally, the output layer outputs, what's the chance of this being 1 versus 0? So let's step through the sequence of computations that the neural network would need to make to go from the input X, this 8 by 8 or 64 numbers, to the predicted probability A3. The first computation is to go from X to A1, and that's what the first layer or the first hidden layer does. It carries out a computation of A superscript square bracket 1 equals this formula on the right. Notice that A1 has 25 numbers because this hidden layer has 25 units, which is why the parameters go from W1 through W25 as well as B1 through B25. And I've written X here, but I could also have written A0 here because by convention, the activation of layer 0, that is A0, is equal to the input feature value X. So that lets us compute A1. The next step is to compute A2. Looking at the second hidden layer, it then carries out this computation where A2 is a function of A1 and is computed as the sigmoid activation function applied to W dot product A1 plus the corresponding value of B. Notice that layer 2 has 15 neurons, or 15 units, which is why the parameters here run from W1 through W15 and B1 through B15. Now we've computed A2. The final step is then to compute A3. And we do so using a very similar computation, only now this third layer, the output layer, has just 1 unit, which is why there's just 1 output here. So A3 is just a scalar. And finally, you can optionally take A3 subscript 1 and threshold it at 0.5 to come up with a binary classification label. Is this the digit 1? Yes or no? So the sequence of computations first takes X and then computes A1 and then computes A2 and then computes A3, which is also the output of the neural network. So you can also write that as f of X. So remember when we learned about linear regression and logistic regression, we use f of X to denote the output of linear regression or logistic regression. So we can also use f of X to denote the function computed by the neural network as a function of X. Because this computation goes from left to right, you start from X, then compute A1, then A2, then A3. This algorithm is also called forward propagation because you're propagating the activations of the neurons. So you're making these computations in the forward direction from left to right. And this is in contrast to a different algorithm called backward propagation or backpropagation, which is used for learning. And that's something you learn about next week. And by the way, this type of neural network architecture, where you have more hidden units initially, and then the number of hidden units decreases as you get closer to the output layer, that's also a pretty typical choice when choosing neural network architectures. And you see more examples of this in the practice lab as well. So that's neural network inference using the forward propagation algorithm. And with this, you'd be able to download the parameters of a neural network that someone else had trained and posted on the internet. And you'd be able to carry out inference on your new data using their neural network. Now that you've seen the map and the algorithm, let's take a look at how you can actually implement this in TensorFlow. Specifically, let's take a look at this in the next video.
他乡带你回家吧。Los tonka broca, las palmas me parier， 今生相见定有亏欠，前世不欠，今生不欠。台下人走过，不见旧颜色，台上人唱着心碎离别歌，是一阵水袖起落，唱悲欢，唱离合，无关我。山开合，锣鼓响幽默，戏中情，戏外人，凭谁说？关将喜怒哀乐都融入粉墨，春季长船又如何？白骨青灰皆我。乱世浮萍，人看烽火燃山河，位卑未敢忘忧国，哪怕无人知我。台下人走过，不见旧颜色，台上人唱着心碎离别歌，情字难落寞，他常书一血来和，谢幕起，戏幕落，谁是客？水袖起落，唱悲欢，唱离合，无关我。山开合，锣鼓响幽默，戏中情，戏外人，凭谁说？关将喜怒哀乐都藏入粉墨，沉寂长船又如何？白骨青灰皆我。乱世浮萍，人看烽火燃山河，位卑未敢忘忧国，哪怕无人知我。台下人走过，不见旧颜色，台下人唱着心碎离别歌，情字难落寞，他常书一血来和，戏幕起，戏幕落，终是客。 想念说的话，铺在天空，灯还有线扫它。遥远的凡人分了帕迪达，为闷在痛也不会害怕。远走的风沙去谁的天涯？春天可曾在哪里讲过它？谁牵的手拂过了连接？他们谁都沉默不说话。我期望许过的愿望，一路生活，护送那谁的门抵挡过风霜。指尖的樱花，如是写谁的韶华？疯狂的热爱夹带着温雅。我希望许过的愿望，一路升华，将那雨中的人藏在屋檐下。岁月在重说逆流沧桑的喧哗，安静的夜晚，你在想谁吗？远走的风沙去谁的天涯？春天可曾在哪里讲过它？时间的手拂过了连接，他们谁都沉默不说话。我期望许过的愿望，一路升华，护送那谁的门抵挡过风沙。指尖的樱花，如是写谁的韶华？疯狂的热爱夹带着微妙。我期望许过的愿望，一路升华，将那雨中的人藏在屋檐下。岁月在重说逆流沧桑的喧哗，安静的夜晚，你在想谁吗？安静的夜晚，你在想谁吗？只叹他回眸，秋水背影去，只忆他颠簸，去日苦多。解三两苦酒，方知离不可。只叹他将思念摇落，心多憔悴，爱付于东流的水，生命分配比不过天公不作美。往事回味，不过是弹指一挥，日复日望穿秋水，恕我愚昧。你爱着谁？心徒留几道伤。我锁着眉，最是相思断人肠。老燕纷飞，寂寥的夜里泪两行。烛短遗恨长，故人自难忘。你爱着谁？心徒留几道伤。 天涯各一方，冷月空对，满腹愁无处话凄凉。我爱不悔，刻骨应难成双。你爱着谁？心徒留几道伤。我锁着眉，最是相思断人肠。流言纷飞，寂寥的夜里泪两行。烛短遗憾，长故人自难忘。你爱着谁？心徒留几道伤。爱多可悲，恨彼此天涯各一方。冷月空对，满腹愁无处话凄凉。我爱不悔，刻骨应难成双。你爱着谁？心徒留几道伤。我锁着眉，最是相思断人肠。劳燕分飞，寂寥的夜里泪两行。烛短遗憾，长故人自难
熬过了风雪，熬过了冬天，偏偏我熬不过这场思念。熬过了黑夜，熬过了失眠，可我熬不过没你在身边。
TensorFlow is one of of the leading frameworks for implementing deep learning algorithms. When I'm building projects, TensorFlow is actually the tool that I use the most often. And the other popular tool is PyTorch. But we're going to focus in this specialization on TensorFlow. In this video, let's take a look at how you can implement inference in code using TensorFlow. Let's dive in. One of the remarkable things about neural networks is the same algorithm can be applied to so many different applications. So in order, both for this video and in some of the labs, for you to see what a neural network is doing, I'm going to use another example to illustrate inference. So sometimes I do like to roast coffee beans myself at home. My favorite is actually Colombian coffee beans. So can a learning algorithm help optimize the quality of the beans you get from a roasting process like this? When you're roasting coffee, two parameters you get to control are the temperature at which you're heating up the raw coffee beans to turn them into nicely roasted coffee beans, as well as the duration or how long you're going to roast the beans. And in this slightly simplified example, we've created the data sets of different temperatures and different durations, as well as labels showing whether the coffee you roasted is good tasting coffee, where cross here, the positive class, y equals 1, corresponds to good coffee, and O, the negative class, corresponds to bad coffee. So it looks like a reasonable way to think of this data. In order, both for this video and in some of the labs, for you to see what a neural network is doing, I'm going to use another example to illustrate inference. So sometimes I do like to roast coffee beans myself at home. My favorite is actually Colombian coffee beans. So can a learning algorithm help optimize the quality of the beans you get from a roasting process like this? When you're roasting coffee, two parameters you get to control are the temperature at which you're heating up the raw coffee beans to turn them into nicely roasted coffee beans, as well as the duration or how long you're going to roast the beans. And in this slightly simplified example, we've created the data sets of different temperatures and different durations, as well as labels showing whether the coffee you roasted is good tasting coffee, where cross here, the positive class, y equals 1, corresponds to good coffee, and O, the negative class, corresponds to bad coffee. So it looks like a reasonable way to think of this data set is if you cook it at too low a temperature, it doesn't get roasted and it ends up undercooked. If you cook it not for long enough, the duration is too short. It's also not a nicely roasted set of beans. And finally, if you were to cook it either for too long or for too high a temperature, then you end up with overcooked beans. They're a little bit burnt beans. And so that's not good coffee either. And there's only points within this little triangle here that corresponds to good coffee. This example is simplified a bit from actual coffee roasting, even though this example is a simplified one for the purpose of illustration. There have actually been serious projects using machine learning to optimize coffee roasting as well. So the task is, given a feature vector X with both temperature and duration, say 200 degrees Celsius for 17 minutes, how can we do inference in a neural network to get it to tell us whether or not this temperature and duration setting will result in good coffee or not? It looks like this. We're going to set X to be an array of two numbers, the input features, 200 degrees Celsius and 17 minutes. Then you create layer 1 as this first hidden layer of the neural network as dense, open parenthesis units 3, that means 3 units or 3 hidden units in this layer, using as the activation function, the sigmoid function. And dense is another name for the layers of a neural network that we've learned about so far. And as you learn more about neural networks, you learn about other types of layers as well. You create layer 1 as this first hidden layer of the neural network as dense, open parenthesis units 3, that means 3 units or 3 hidden units in this layer, using as the activation function, the sigmoid function. And dense is another name for the layers of a neural network that we've learned about so far. And as you learn more about neural networks, you learn about other types of layers as well. But for now, we'll just use the dense layer, which is the layer type you've learned about in the last few videos for all of our examples. So next, you compute A1 by taking layer 1, which is actually a function, and applying this function layer 1 to the values of x. So that's how you get A1, which is going to be a list of 3 numbers because layer 1 had 3 units. And so A1 here may, just for the sake of illustration, be 0.2, 0.7, 0.3. Next, for the second hidden layer, layer 2 would be dense of, now this time it has 1 unit, and again, the sigmoid activation function. And you can then compute A2 by applying this layer 2 function to the activation values from layer 1 to A1, and that will give you the value of A2, which for the sake of illustration is maybe 0.8. Finally, if you wish to threshold this at 0.5, then you can just test if A2 is greater than or equal to 0.5 and set y hat equals to 1 or 0, positive or negative class accordingly. So that's how you do inference in the neural network using TensorFlow. There are some additional details that I didn't go over here, such as how to load the TensorFlow library and how to also load the parameters W and B of the neural network, but we'll go over that in the lab. So please be sure to take a look at the lab. But these are the key steps for propagation and how you compute A1 and A2 and optionally threshold A2. Let's look at one more example, and we're going to go back to the handwritten digit classification problem. So in this example, X is a list of the pixel intensity values. So X is equal to a NumPy array of this list of pixel intensity values. And then to initialize and carry out one step before propagation, layer 1 is a dense layer with 25 units and the sigmoid activation function. And you then compute A1 equals the layer 1 function applied to X. To build and carry out inference through the second layer, similarly, you set up layer 2 as follows, and then compute A2 as layer 2 applied to A1. And then finally, layer 3 is the third and final dense layer. And then finally, you can optionally threshold A3 to come up with a binary prediction for y hat. So that's the syntax for carrying out inference in TensorFlow. One thing I briefly alluded to is the structure of the NumPy arrays. TensorFlow treats data in a certain way that is important to get right. So in the next video, let's take a look at how TensorFlow handles data. In this video, I want to step through with you how data is represented in NumPy and in TensorFlow, so that as you're implementing new neural networks, you can have a consistent framework to think about how to represent your data. One of the unfortunate things about the way things are done in code today is that many years ago, NumPy was first created and became a standard library for linear algebra in Python. And then much later, the Google Brain team, the team that I had started and once led, created TensorFlow. And so unfortunately, there are some inconsistencies between how data is represented in NumPy and in TensorFlow. So it's good to be aware of these conventions so that you can implement correct code and hopefully get things running in your neural networks. Let's start by taking a look at how TensorFlow represents data. Let's say you have a data set like this from the coffee example. I mentioned that you would write X as follows. So why do you have this double square bracket here? Let's take a look at how NumPy stores vectors and matrices. In case you think matrices and vectors are complicated mathematical concepts, don't worry about it. We'll go through a few concrete examples and you'll be able to do everything you need to do with matrices and vectors in order to implement neural networks. Let's start with an example of a matrix. Here is a matrix with 2 rows and 3 columns. Notice that there are 1, 2 rows and 1, 2, 3 columns. So we call this a 2 by 3 matrix. And so the convention is the dimension of a matrix is written as the number of rows by the number of columns. So in code, to store this matrix, this 2 by 3 matrix, you just write x equals np dot array of these numbers like these, where you notice that the square bracket tells you that 1, 2, 3 is the first row of this matrix, and 4, 5, 6 is the second row of this matrix, and then this upper square bracket groups the first and the second row together. So this sets X to be this 2D array of numbers. So a matrix is just a 2D array of numbers. Let's look at one more example. Here, I've written out another matrix. How many rows and how many columns does this have? Well, we can count. This has 1, 2, 3, 4 rows, and it has 1, 2 columns. So this is a number of rows by number of columns matrix. So it's a 4 by 2 matrix. And so to store this in code, you would write x equals np.array, and then this syntax over here to store these 4 rows of a matrix in the variable x. So this creates a 2D array of these 8 numbers. Matrices can have different dimensions. You saw an example of a 2 by 3 matrix and a 4 by 2 matrix. A matrix can also be other dimensions like 1 by 2 or 2 by 1. And we'll see examples of these on the next slide. So what we did previously when setting x to be input feature vectors was set x to be equal to np array with 2 square brackets 200, 17. And what that does is this creates a 1 by 2 matrix that is just 1 row and 2 columns. Let's look at a different example. If you were to define x to be np array, but now written like this creates a 2 by 1 matrix that has 2 rows and 1 column, because the first row is just the number 200 and the second row is just the number 17. And so this has the same numbers, but in a 2 by 1 instead of a 1 by 2 matrix. In math, this example on top is also called a row vector. It's a vector that is just a single row. And this example is also called a column vector because it's a vector that just has a single column. And the difference between using double square brackets like this versus a single square bracket like this is that whereas the 2 examples on top are of 2D arrays where one of the dimensions happens to be 1, this example results in a 1D vector. So this is just a 1D array that has no rows or columns. Although by convention, we may write x as a column like this. So I want to contrast this with what we had previously done in the first course, which was to write x like this with a single square bracket. And that resulted in what's called in Python a 1D vector instead of a 2D matrix. And this technically is not 1 by 2 or 2 by 1. It's just a linear array with no rows or no columns. But it's just a list of numbers. So whereas in course 1, when we're working with linear regression and logistic regression, we use these 1D vectors to represent the input features x. With TensorFlow, the convention is to use matrices to represent the data. And why is there this switch in conventions? Well, it turns out that TensorFlow was designed to handle very large data sets, and by representing the data in matrices instead of 1D arrays, it lets TensorFlow be a bit more computationally efficient internally. So going back to our original example, for the first training example in this dataset with features 200 degrees Celsius in 17 minutes, we would represent it like this. And so this is actually a 1 by 2 matrix that happens to have 1 row and 2 columns to store the numbers 217. And in case this seems like a lot of details and really complicated conventions, don't worry about it. All this will become clearer and you get to see the concrete implementations of the code yourself in the optional labs and in the practice labs. Going back to the code for carrying out forward propagation or inference in the neural network, when you compute A1 equals layer 1 applied to X, what is A1? Well, A1 is actually going to be, because there's 3 numbers, is actually going to be a 1 by 3 matrix. And if you print out A1, you will get something like this. Is tf.tensor 0.2.7.3 is a shape of 1 by 3. 1, 3 refers to that this is a 1 by 3 matrix. And this is TensorFlow's way of saying that this is a floating point number, meaning that it's a number that can have a decimal point represented using 32 bits of memory in your computer. That's what a float 32 is. And what is a tensor? A tensor here is a data type that the TensorFlow team had created in order to store and carry out computations on matrices efficiently. So whenever you see tensor, just think of it as matrix on these few slides. Technically, a tensor is a little bit more general than a matrix, but for the purposes of this course, think of tensor as just a way of representing matrices. So remember I said at the start of this video that there's the TensorFlow way of representing a matrix and the NumPy way of representing a matrix. This is an artifact of the history of how NumPy and TensorFlow were created. And unfortunately, there are 2 ways of representing a matrix that have been baked into these systems. And in fact, if you want to take A1, which is a tensor, and want to convert it back to a NumPy array, you can do so with this function, a1.numpy, and it will take the same data and return it in the form of a NumPy array rather than in the form of a TensorFlow array or TensorFlow matrix. Now let's take a look at what the activations output by the second layer would look like. Here's the code that we had from before. Layer 2 is a dense layer with 1 unit and sigmoid activation, and A2 is computed by taking layer 2 and applying it to A1. So what is A2? A2 may be a number like 0.8, and technically this is a 1 by 1 matrix. It's a 2D array with 1 row and 1 column, and so it's equal to this number 0.8. And if you print out A2, you see that it is a TensorFlow tensor with just 1 element, 1 number, 0.8, and it is a 1 by 1 matrix. And again, it is a float 32, decimal point number taking up 32 bits in computer memory. Once again, you can convert from a TensorFlow tensor to a NumPy matrix using a2.numpy, and that will turn this back into a NumPy array that looks like this. So that hopefully gives you a sense of how data is represented in TensorFlow and in NumPy. I'm used to loading data and manipulating data in NumPy, but when you pass a NumPy array into TensorFlow, TensorFlow likes to convert it to its own internal format, the tensor, and then operate efficiently using tensors. And when you read the data back out, you can keep it as a tensor or convert it back to a NumPy array. I think it's a bit unfortunate that the history of how these libraries evolve has led us to have to do this extra conversion work when actually the 2 libraries can work quite well together. But when you convert back and forth, whether you're using a NumPy array or a tensor is just something to be aware of when you're writing code. Next, let's take what we've learned and put it together to actually build a neural network. Let's go see that in the next video. So no, numbers is actually going to be a 1 by 3 matrix. And if you print out A1, you will get something like this. Is tf.tensor 0.2.7.3 is a shape of 1 by 3. 1, 3 refers to that this is a 1 by 3 matrix, and this is TensorFlow's way of TensorFlow. So you see in the TensorFlow. So you've seen a bunch of TensorFlow code by now, learned about how to build a layer in TensorFlow, how to do forward prop through a single layer in TensorFlow, and also learned about data in TensorFlow. Let's put it all together and talk about how to build a neural network in TensorFlow. This is also the last video on TensorFlow for this week. And in this video, you also learn about a different way of building a neural network that will be even a little bit simpler than what you've seen so far. So let's dive in. What you saw previously was if you want to do forward prop, you initialize the data X, create layer 1 like so, then compute A1, then create layer 2 and compute A2. So this was an explicit way of carrying out forward prop one layer of computation at a time. It turns out that TensorFlow has a different way of implementing forward prop as well as learning. Let me show you a different way of building a neural network in TensorFlow, which is that, same as before, you're going to create layer 1 and create layer 2. But now, instead of you manually taking the data and passing it to layer 1, and then taking the activations from layer 1 and passing it to layer 2, we can instead tell TensorFlow that we would like it to take layer 1 and layer 2, and string them together to form a neural network. That's what the sequential function in TensorFlow does, which is it says, "Dear TensorFlow, please create a neural network for me by sequentially stringing together these two layers that I just created." It turns out that with the sequential framework, TensorFlow can do a lot of work for you. Let's say you have a training set like this on the left. This is for the coffee example. You can then take the training data's inputs X and put them into a NumPy array. This here is a 4x2 matrix. And the target labels Y can then be written as follows. And this is just a one-dimensional array of length 4. Y, this set of targets, can then be stored as a 1D array like this, 1001, corresponding to 4 training examples. And it turns out that given the data X and Y stored in this matrix X and this array Y, if you want to train this neural network, all you need to do is call two functions. You need to call model.compile with some parameters. We'll talk more about this next week, so don't worry about it for now. And then you need to call model.fitxy, which tells TensorFlow to take this neural network that it created by sequentially stringing together layers 1 and 2 and to train it on the data X and Y. But we'll learn the details of how to do this next week. And then finally, how do you do inference on this neural network? How do you do forward prop? If you have a new example, say XNew, which is NP array with these two features, then to carry out forward prop, instead of having to do it one layer at a time yourself, you just have to call model predict on XNew, and this will output the corresponding value of A2 for you, given this input value of X. So model predict carries out forward propagation or carries out inference for you using this neural network that you compiled using the sequential function. Now, I want to take these 3 lines of code on top and just simplify it a little bit further, which is when coding in TensorFlow, by convention, we don't explicitly assign the 2 layers to 2 variables, layer 1 and layer 2, as follows. But by convention, I would usually just write the code like this, where we say the model is a sequential model of a few layers strung together sequentially, where the first layer, layer 1, is a dense layer with 3 units and activation of sigmoid, and the second layer is a dense layer with 1 unit and again a sigmoid activation function. So if you look at others' TensorFlow code, you often see it look more like this, rather than having an explicit assignment to these layer 1 and layer 2 variables. And so that's it. This is pretty much the code you need in order to train as well as do inference on a neural network in TensorFlow, where again, we'll talk more about the training bits of this, the compile and the fit function next week. Let's redo this for the digit classification example as well. So previously we had X is this input, layer 1 is a layer, A1 equals layer 1 applied to X, and so on through layer 2 and layer 3 in order to try to classify a digit. With this new coding convention, with using TensorFlow's sequential function, you can instead specify what are layer 1, layer 2, layer 3, and tell TensorFlow to string the layers together for you into a neural network. And same as before, you can then store the data in a matrix and run the compile function and fit the model as follows. Again, more on this next week. And finally, to do inference or to make predictions, you can use model predict on X new. And similar to what you saw before with the coffee classification network, by convention, instead of assigning layer 1, layer 2, layer 3 explicitly like this, we would more commonly just take these layers and put them directly into the sequential function. So you end up with this more compact code where you just tell TensorFlow, create a model for me that sequentially strings together these 3 layers, and then the rest of the code works same as before. So that's how you would build a neural network in TensorFlow. Now, I know that when you're learning about these techniques, sometimes someone may ask you to, hey, implement these 5 lines of code. And then you type 5 lines of code, and then someone says, congratulations, with just 5 lines of code, you built this crazy complicated state-of-the-art neural network. And sometimes that makes you wonder, what exactly did I do with just these 5 lines of code? One thing I want you to take away from the machine learning specialization is the ability to use cutting-edge libraries like TensorFlow to do your work efficiently. But I don't really want you to just call 5 lines of code and not really also know what the code is actually doing underneath the hood. So in the next video, I'd like to go back and share with you how you can implement from scratch by yourself forward propagation in Python so that you can understand the whole thing for yourself. In practice, most machine learning engineers don't actually implement forward prop in Python that often. We just use libraries like TensorFlow and PyTorch. But because I want you to understand how these algorithms work yourself, so that if something goes wrong, you can think through for yourself what you might need to change, what's likely to work, what's less likely to work. Let's also go through what it would take for you to implement forward propagation from scratch. Because that way, even when you're calling a library and having it run efficiently and do great things in your application, I want you in the back of your mind to also have that deeper understanding of what your code is actually doing. So let's go on to the next video.